Light shouldn't look like a tornado. It doesn't have wind, it doesn't have clouds, and obviously there's no tiny storm spinning around inside a laboratory. But give scientists the right laser equipment, and light can start doing something that looks completely wrong. It can twist, not just curve slightly. We're talking about light arranged into a corkscrew-like structure with a dark center, creating what's known as an optical vortex. And once researchers figured out how to control these things, they realized the weird shape wasn't just something cool to look at. They could actually use it to manipulate microscopic objects. So how do you turn a beam of light into something resembling a tiny tornado? First, forget the laser pointer you've got sitting in a drawer somewhere. A normal laser beam is basically sending light in one organized direction. But light is a wave, and scientists can manipulate the phase of that wave. Using specially designed optical components, researchers can make different parts of the beam advance at different phases. Do that correctly, and the wavefront begins wrapping around itself like a corkscrew. Right in the center, something strange happens. The waves interfere in a way that leaves a dark spot. There's essentially no light intensity at the exact center. Surrounding that darkness is a ring of light carrying something called orbital angular momentum. That's the key, because angular momentum means that when this light interacts with matter, it can transfer some of that rotational motion. In plain English, light can make tiny things spin. And that's where I went from, okay, that's a cool laser trick, to, wait, you can actually do something with it? Researchers can use focused light to trap microscopic particles. You've probably heard of optical tweezers. Instead of grabbing something with metal jaws, scientists use the forces produced by highly focused laser light to hold and move incredibly small objects. The technique became so important that work on optical tweezers earned part of the 2018 Nobel Prize in Physics. Now add twisted light to that idea. Instead of simply holding a microscopic object, you can potentially rotate it. Picture trying to grab something smaller than a human cell. Your fingers are useless. Even ordinary mechanical tools become enormous at that scale. Light doesn't have that problem. A carefully controlled beam can interact with tiny particles without needing a physical hand anywhere near them. That opens up some wild possibilities. Researchers can manipulate microscopic beads used in experiments. They can study tiny biological structures. They can investigate how microscopic objects respond to forces. And these optical vortex techniques have potential applications across areas like microfluidics, advanced imaging, communications, and fundamental physics. But here's where the story gets even stranger. Twisted light isn't only useful for moving objects, it can also carry information. Different twisted states of light can potentially represent different channels of data. Instead of only asking whether light is on or off, or what frequency it's using, engineers can exploit the structure of the beam itself. Think about a highway. Normally, if you want more traffic moving through an area, you need more lanes. Twisted light gives researchers another property they can potentially use to separate information into additional channels. That could help increase the amount of data carried through certain optical communication systems. Now I need to ruin the coolest mental image before somebody starts looking outside for a glowing laser hurricane. We're not talking about a tornado in the normal weather sense. There's no miniature funnel cloud tearing apart a laboratory. Optical vortex describes the structure and phase of the light. The tornado comparison helps visualize the twisting pattern, but the underlying physics is completely different from a storm. And these effects are generally happening at extremely small scales under carefully controlled conditions. Still, I think the real version is actually cooler. Because humans have gotten so good at controlling light that we're no longer satisfied with simply turning it on, focusing it, or changing its color. We're shaping its internal structure. We're giving it angular momentum. We're using it to grab things we can't touch, spin things too small to hold, and potentially carry information in ways ordinary beams can't. Think about how far that idea has come. For most of human history, light was just something that let us see. Then we learned how to focus it. Then came lasers, then fiber optic communication, then optical tweezers. Now we're deliberately twisting light into controlled vortices and using those structures as tools. And we're probably nowhere near finished. That's what makes photonics so fascinating. The beam coming out of a laser might look simple, but once scientists start manipulating the properties hidden inside it, light becomes less like illumination and more like a machine. No gears, no motor, nothing you could reach out and grab. Just carefully controlled photons doing work on objects you can barely even see. So the next time somebody tells you light only travels from point A to point B, you might want to show them what happens when scientists teach it to twist.